Okay, welcome ladies and gentlemen. You might be wondering, why am I looking at a deflating balloon? Well, it's because what we're looking at today is all about how things change and how they're related to each other. We're looking at a topic called related rates. And with that balloon, air is leaking out, which means the volume of the air in the balloon is changing. But if you notice, the balloon was getting smaller, which means the surface area of the balloon was also changing. And what we're studying now is how are those two rates related to each other. Hopefully you can rationalize that they definitely are related to each other, because as one changes, the other also has to change. So we're going to look at a couple of examples today and see if we can't get a handle wrapped around how we calculate related rates. If you don't have an understanding of implicit differentiation, this section is going to be very difficult for you. So I would make sure I go back and revisit implicit differentiation before I get too far into this. So we have a ladder leaning against the building. It starts to slip down, and it's slipping down at a rate of 1/2 meters per second. How fast is the foot of the ladder, the other end of the ladder, moving along the ground at the instant in time that it's 6 meters from the wall? So let's draw a picture. So here's my building, and up against that building there is a ladder. And there's the ground. The ladder is 10 meters, always 10 meters. We have the distance from the building, I'll call it X. And we have the distance up the wall it goes, I'll call it Y. What's changing as this ladder falls? How do you think, what things are rates as this ladder slides down the wall? Well, Y changes as time goes on. So we have a dy dt, and we have dx dt. Both of those distances are changing as time goes on. So neither one of those are constant, so we're going to have differentials for each of those in this problem. Now, I drew a picture, I labeled it. How are the labels in this picture related? Well, this is a right triangle, ladies and gentlemen. We can use the Pythagorean Theorem, x squared plus y squared equals 10. Now, we're given the condition that 6 meters from the wall. That's when x is equal to 6. So when x equals 6, it might be nice to know what y is. So 36 plus y squared equals 100. Y ends up being 8. Cool, but I haven't done any calculus, have I? So the calculus is going to happen right here. We're going to take the derivative of this relationship between the sides. And we're going to take the derivative of the first term, 2x, but we have to multiply by dx dt, because x is changing as time passes. So we have implicit differentiation. And then 2y dy dt, because y is also changing as time goes on, equals 0. Now we know that dy dt is equal to negative 0.5. Why negative, you might ask? Well, because it's going down the side of the building. We're sort of treating this as a coordinate plane. Down would be negative. Left would be negative. So what do we do? Well, the only thing we don't know at this point is dx dt. We can substitute, we can solve. 2 times 6 dx dt plus 2 times 8 times negative 0.5 equals 0. So we have 12 dx dt equals 8. So dx dt is equal to positive 2/3 meter per second. And that's positive. It's a positive rate. That should make sense. That end of the ladder is moving away from the building. So there we go. We drew a picture. We wrote a function or an equation describing, modeling the picture. We found the values of the different pieces of that picture at the instant in time that we care about. And we differentiated before substituting these values. And notice I did not substitute x and y in here because that wouldn't accomplish anything. We have to wait until after we differentiate so that we can find the rates at the instant in time that we are looking for, which is what these numbers are. So here's example number 2. We have water being poured into a conical tank at the rate of 3 cubic meters per minute. The tank stands with the point downward. So first things first, I'm going to draw myself a picture. And water is being poured in to this conical tank at a rate of 3 cubic meters per minute. So that would be dV dt is 3. Excellent. Then it says, how fast is the water level in the tank rising when the depth is 2 meters and the radius of the surface of the water surface is 1.5? Okay, so we need to draw a little bit more. So we're going to have water in this tank. Like that. This is water, and we're told we care about this when the depth is 2 meters. We'll call it D, or maybe instead of calling it D, let's use a letter that's more familiar to us when it comes to finding volumes. Let's call it H for height of this cone, because the water is just a mini cone in here. And then we have a radius in here. R equals 1.5 at that instant in time. Okay, so, what are we looking for? Well, we're looking for dH dt, nifty. What else do we know? Do we know anything else here? Well, we know volume of a cone is 1/3 area of the base times the height. And how do we find the area of the base here? Well, it's 1/3 pi r squared times h. So here is a formula relating to the problem that I was given. So let's find how all these rates are related to each other. So we're going to differentiate with respect to time. We're wondering how things are changing as time goes on. So on the left side we have dV dt equals, now for the fun. What do we really have on the right-hand side? On the right-hand side we have 1/3 pi, that's a constant, times r squared times h. And both h, the height of the water, and r, for the top of this water, both of those quantities are changing as time goes on. So we have to use implicit differentiation here, and we have to use the product rule. So 1/3 pi times first times derivative of the second, plus second times derivative of the first, and the derivative of the first is going to be 2r dr dt. And here is our derivative of that volume function with respect to time. And let's look at what we have. We know dv dt. We know our value of r. We're looking for dh dt. We know a value of h for the instant in time, and same with r, but we don't know dr dt. We actually know nothing about that. So, oh boy, this gets quite a bit more difficult. But we've studied geometry, and we know that similar triangles, their dimensions are always in proportion to each other. So if I were to jump over here, here's R and H, and the triangle that I have in my picture has a radius of 1.5 and an H equal to 2, we could write a proportion for this. H is to 2 as R is to 1.5, so 1.5 H equals 2R, and R, therefore, is equal to 0.75 H. And you might be saying, well, great, who cares? You knew R and you knew H for this, but what this allows me to do is differentiate this. I have a relationship between R and H. I can find dr dt. Dr dt is equal to 0.75 dh dt, and that allows me, ladies and gentlemen, to make a nice, glorious substitution right there. And now we know every piece of this derivative, and the only thing I'm missing is dh dt, the thing that I was trying to solve for. So let's substitute the numbers and do our solving. In doing these substitutions and solving, you should find that dh dt is equal to 0.424 meters per minute. We're looking for relationships between the variables, between the differentials. We're trying to relate the rates. If we come to a spot where we don't have all the information, you need to try and find new relationships, like I did with the similar triangles over here. And that's where I leave you. Some of these problems do get a bit involved. Don't be scared off by the length of the work that you sometimes have to put in.